We're talking about dienes. Dienes are popular, dienes are common. There's always this sort of geeky sense of humor that comes out with these things. You'll probably see that around if you study this stuff. They're important types of compounds. We talked about this on Monday, and I want to just go over it again quickly to make sure that we understand this molecular orbital theory so we can use it in the near future to do reactions. We talk about the different types of diene. We talk about sort of isolated dienes. We talk about conjugated dienes. And the difference does make a huge difference in terms of their chemistry. On the left, we have the isolated, which just act as if there were simple alkenes. They would do the same chemistry you've seen before. On the right, you'll see a difference. If you have this conjugated diene system now, you will see a difference in reactivity. We talked about these pictures. I'm going to sort of spend a few minutes on these again so that people are happy with this idea. We can represent the p orbitals as the usual dumbbell shape, as you've learned from high school onwards, I hope, and talk about their relationship to each other. And the fact that at the bottom, we have this sp3 carbon in the middle. That would be a big deal. That blocks the conjugation. The two pi bonds cannot talk to each other, and they act as if they were separate pi bonds. As opposed to this one, in which we have the two middle p orbitals next to each other, then they can communicate. So this conjugation idea is all about communication on the left side and the right side in terms of the p orbital. You can get overlaps in different directions, and that gives the conjugated diene, which we say is more stable. In terms of how you make them, pretty straightforward. E1s, E2s, we dealt with that pretty quickly. Some evidence for the fact that we do have a shorter bond in the middle. It is not necessarily a single bond or a pi bond. It's somewhere in between. We can look at things like crystallography and measure these values. The bond in the middle there on the left is shorter than a regular CC bond, and that's because of the overlap between the p orbitals. Some proof for the engineers, some numbers. We can see here that a pi bond is worth half of 254. Two of those is 254, and that's the energy released if you hydrogenate two individual pi bonds. Well, if you look at this molecule on the right, it certainly has two pi bonds, or it seems to, but the number released is less. The amount of energy is released is less. That means the molecule is more stable to start with, and that's the conjugation energy. That's the energy that is sort of built into the fact that this thing can communicate across the four p orbitals. So the diene chapter is leading into the 6-carbon system, which is much more complicated. So we need to understand some of these diagrams that we've been drawing. This idea is fairly straightforward, the idea of S-cis and S-trans. We've got to worry about whether your compound is one of those two shapes, because then when we talk about the Diels-Alder reaction today, you'll recognize that only S-cis types of systems will do this. The S-trans will not react under this type of condition. And we started talking about the energy diagrams, and we talked about the relationships between these two types of ideas. It's the same molecule, it's just a different shape. So it's very much like the Newman depiction type last year type of ideas, the anti and the eclipse and all that type of thing. We have two different shapes, they're related because it's the same molecule. We have a barrier to that rotation, and that barrier is significant. That 15 kilojoules per mole is the energy it takes for the single bond to rotate, right? That's much more than it is in a simple alkane, and that's because we have pi character between the two central carbons. Now what we left off with was a discussion really of this idea of molecular orbital theory. And I would assume you would get this in the freshman class, and I'd assume that you would understand it at this point. We're going to go over it again just in case we don't. This goes all the way back to the first week of class last term, in which we had the idea of a hydrogen molecule coming together. On the left, we started talking about representations of orbitals. There's an s orbital, there's an s orbital. Those two are hydrogen atoms. And the reason hydrogen atoms overlap is to become a more stable hydrogen molecule, where we have the inert gas type configuration. And we've got to remember that when these two things overlap, we can have two possibilities. One in which they overlap in a sort of a positive sense and a constructive interference sense, and you get a bond. And the other one, which we sort of have ignored for now at least, is the antibond. They're both there. We've got to remember that space, that antibond is there if we need it, and we will need it in the near future. So the two electrons, 1s, 1s, go into the bond, and that's typically what we draw when we write this, and we abbreviate things, and we get into all of these line structures. Those two electrons now are that line. And that benefits both atoms because now we have the stable configuration of a noble gas. Well, when we extrapolate that to alkenes, it's no different. You have two orbitals coming together. Obviously, with a diene, you're going to get four orbitals coming together. It's just an extension of that idea. So stop me if you don't get this stuff, and ask me in recitation or in office hours. It's important that we do see what we're trying to show here. This is the picture for a pi bond. Now, for a pi bond, we're not talking about sigma orbitals anymore. We're talking about p orbitals. So the shape has changed. We're no longer spherical. We're now this dumbbell shape. But now again, we have a single 2p orbital from one atom and a single 2p orbital from another atom. And you might imagine this is an attempt to show a molecule like ethene, in which we are overlapping the 2p orbitals to make a pi bond. It's the same idea. You start off with atomic orbitals here and here, both of which have one electron. That's the requirement for a pi bond, right? parallel p orbitals, both of which are pointing in the same direction and have about the same size and have one electron each. And if these things overlap, we can form a bond. So again, this system here is when the two electrons have ended up in the same orbital. We now have what we call a pi bond, and that's represented by that, or in simple line structures like that, C double bond C. Everybody's okay with that, yeah? Nothing tricky there. Well, we also have, let's call this pi, and let's call this pi star. That's the antibond in which we could put an electron if we're able to put some energy in and promote the electron. If you could push the electron from the bottom to the top, it would have to go somewhere. And I've always understood this to be, okay, if this orbital isn't there, and I do promote that electron, it would just fly off. What's that? If an electron flies off something, what's that called? Ionization. Ionization, right? And if we're not going to ionize molecules here, it just doesn't happen. So we have to have some place to put that electron temporarily, and we'll see it's called the pi star orbital, and that's important now that you understand that the antibond orbital is there and it's real. So we've got some definitions here in terms of the p orbital system. It is absolutely very similar to the s orbital system, just that we've changed the shape of the orbitals. So for the simple alkene, it mirrors pretty much the 1s interaction for a simple hydrogen molecule. Now, what we have to do very quickly is get into these more complex structures because we have 4 p orbitals in a row. We have the conjugated system. And what I tried to explain on Monday was that if you have 4 atomic orbitals, you must make 4 molecular orbitals. You conserve. You can't destroy these molecular orbitals. So if I've got 4 of these things at the sort of 0 point, and if I draw across here, this is the point at which we don't have any communication. All right? This is just p orbitals, and they're empty, and we're going to start putting them together. Now, the best possibility is when everything talks to each other, when you have communication in all directions possible, left and right. And that's going to give you what we'll call down here, we usually call it something like that, pi 1, pi 2. And then above, pi star 1 and pi star 2. You might see that sort of notation elsewhere. At the bottom, we have the best situation in which all of those orbitals overlap and interact. Why is that the best situation? Because that's complete bonding. Everything's bonding, you have the maximum interaction. And we can draw that. Let me go back. We can draw that in several different ways. If you're artistic, you can draw this. You can show the conjugation there. But typically we would draw these pictures, and I'm leading to benzene. Benzene is more complicated again, and I'd like you to be okay with this stuff. On the right-hand side, I have 4 p orbitals in which the lobes are all matching, and simply represented by the color of the lobes. All the red are lined up, and all the blue are lined up. That's said to be completely in phase, maximum constructive interference. That is the best possible situation for that molecule. Well, that's only one of them. I need 3 more. And the way this is understood now, to be able to put them together, is to go to a higher energy. A higher energy means less stable, and so less stable should mean less bonding. And that's shown by this, what we call a node. And a node is simply the break in communication between some of the atoms. The central 2 atoms are not talking to each other. Now, we just tried to show that with the experiment showing the different hydrogenation energies. You'd have to say that this down here is complete conjugation. This here is still bonding, but there's no communication in the middle. So this is the situation where maybe this is a pi bond, and this is a pi bond, which is completely fine and stable, but they're not talking to each other in the middle. So that's pi 2. Now, to go above the 0 point, we have to think about instability. The ones above the 0 point are going to become unstable. So I'm going to have less communication. In this case, I've got a situation with now 2 nodes, and it does go up, 1, 2, 3, as you head up. We now have 2 breaks in communication, so less bonding again. And in this case, we'll see it's actually unstable. We only have the 1 pi situation in the middle, and we have 2 of these things. And if I put electrons in those things, they're radicals. That would be a diradical, and that would be very unstable. So it's above the 0 point. If I go to the top, we have complete lack of communication. Okay? All of the phases are out of phase. You could represent this, as I will in recitation, with just coloring in one of the orbital lobes, and then seeing if they match or they don't. It's very easy to represent. Hopefully understood as well. Well, I've got 4 electrons. I've now done my 4 orbitals. I've got 4 electrons. 2, 1 from each of these. And we've got 4 of them. Electrons fill up singly before they double up. You can only put 2 electrons in one orbital at any one time. And so it makes sense that 2 of them go down here. Don't forget the little arrows are the electrons. 2 at the bottom. And in this case, 2 in the second orbital, like so. The whole point of this molecule is that we can put those electrons into bonding orbitals so that the system is stabilized by these interactions. We don't need to put any electrons into the higher orbitals, which would destabilize. We will do that soon, but right now we're talking about a stable system. Definitions for the near future. This is unoccupied. This is occupied, right? This is the highest energy occupied molecular orbital. We'll see why that's important soon. This is the lowest unoccupied molecular orbital. Now, you can teach this entire 2-semester sequence just with these ideas, just with these pictures. There are textbooks that will take that approach, molecular orbital approach, and it's kind of interesting to do it that way. We will use, for the most part, as we have in the past, that type of depiction. Those arrows kind of take away some of this necessity to draw all these pictures all the time. But if I'm talking about putting electron density in different places, and let's say I've got two molecules reacting, is this a sensible thing to do? I've got a pair of electrons on the left attacking a pair of electrons on the right. Is that a sensible thing to do? No, because you can only put two electrons in one orbital at one time. So when I get to this situation fairly soon, it's going to be obvious that this highest occupied molecular orbital ought to interact with that lowest unoccupied molecular orbital, because that has space. And if I do that, thinking about the chemistry that's about to happen, if I put electrons here, does that stabilize or destabilize the overall system? It destabilizes it. You put it into an antibonding situation. So do I go up or down on a reaction profile? Up. If you're always wondering about why we go up in reaction profiles, it's because of this idea. We're putting electrons in bad places. And then the system reorganizes itself. You think about what transition states are. It's all about reorganization of atoms in space. And the system reorganizes itself to become more stable, right? So the initial interaction between, let's say, a nucleophile and an electrophile is the highest occupied molecular orbital of the nucleophile going after the lowest unoccupied molecular orbital of the electrophile. That's how it works. Again, you can do the whole 2 semesters like that. We don't have that luxury just yet, but this is important now for these diene systems. There are definitions, nodes, understand what a node is, understand to draw these pictures. I think it's much better if you know how to do this rather than memorize how to do this. Because when you get to 6 atoms and you start talking about benzene, then it gets kind of confusing if you try to memorize things. You forget, you get lost. If you understand how it's working here, then it's pretty straightforward. So I've got some pictures here that show the definitions. On the top, you've got the highest occupied molecular orbital, and it is going to be the one that reacts with the incoming species, whatever that happens to be in the near future. So we talked about the use of these types of ideas then to do chemistry. If you think about this reaction, we have that happening. In the language that I just tried to use to at least get us started, this is a nucleophile, right? And those 2 electrons have to come from someplace. Where do they come from? We only have 2 orbitals here. In the system for an alkene, you only have 2 orbitals. One is pi, and one is pi star. So where do the electrons come from for that interaction? The pi bond, the pi orbital, the bonding orbital, right? So keep an eye on that sort of thing. Now, the mechanism there is Markovnikov. The mechanism there is trying to show you again that you get the better carbocation whenever you can. In this case, tertiary over primary, and that gave you a very simple addition of HBr that we dealt with last year in order to make substituted halides, such as tertiary alkyl halides. Well, the big thing today is to worry about the addition of HBr to a diene. It is way more complicated because you have that second pi bond right there. Same principles, Markovnikov is good. The idea you want the best carbocation. Not only will the carbocation be helped now by hyperconjugation, it will be helped by resonance. And that makes a big difference. So the picture here is showing again what we call a 1,2 product and what we call a 1,4 product. With HBr you get both. Depending upon the structure of the molecule, you'll typically get both. And the chemistry here, it doesn't matter if I start from this end or this end, because in this case it's symmetrical. And I get the first protonation. Now, in the past we've argued, well, if you have a tertiary versus a secondary, you'll get some of both. If you have a tertiary carbocation versus a primary carbocation, you'll only get the tertiary. In this example, you're only going to get this system because it's allylic and it's stabilized by resonance. You're not going to see any of that molecule where you protonate it internally and you put the charge at the end, for several reasons. Number one, this charge is not, it's primary, that's terrible, and it's not allylic, right? It's too far away from the pi bond to actually get any help from the pi bond. So you're not going to see that product at all. What we are going to see is the potential now for this carbocation, stabilized through resonance, to have 2 positive carbons. Or let's say 2 delta positive carbons, because it's 1 positive charge shared over the system. We now have a situation in which the electrophile can be attacked at 2 places, and that's a big thing about to happen in a bunch of different reactions. So this nucleophile now has a choice of where to go. If the nucleophile adds here, we get this 1,2 product. If the nucleophile adds here, we get the 1,4 product. That's the outcome. Same thing happens with Br2. There's the mechanism. I'll show you this again. You're going to spend a lot of time on this in the near future. Same thing happens for bromine. You get the same outcome. We have to understand why we can do this and how we can control this with temperature. So there are two things to get through today. Number one is this slide, understand what it's about and how this works, and then the Diels-Alder reaction. Well, what's happening here? The same compound. We're setting up 3 experiments, if you like. You have 3 flasks in the lab, and you're mixing the diene with HBr in each of them. And what's changing in each of them is the temperature. The conditions are all the same in terms of concentration and the amounts that you've used, but we're changing the temperature. And simply from going from -80, which is quite easy to do, you take some dry ice, you put it in acetone, that gives you a roughly -80 temperature. You put your flask in there, you run your reaction, you finish this thing, and you get that outcome. You get about 4 to 1, in which the 1,2 product is favored and the 1,4 product is minor. So we can go back and use those terms again. The 1,2 is major, the 1,4 is minor. Next flask along, we're running at room temperature. This now gives the same products, however, the ratio has changed. You're getting closer to a 1-to-1 mixture, in which the 1,2 now is diminished, and the 1,4 there's more of it. At the bottom, go higher, change this up to about 45 degrees, maybe reflux it in some solvent, and we get much less of this, and we get that now. So look at that, it's gone completely the opposite direction, simply through a temperature change. And the reason we talk about this is to get you ready for some of the biochem you have to start thinking about in the future, and think about the terms kinetic versus thermodynamic. What is the reaction controlled by? Is it controlled by how fast it happens, or is it controlled by how stable the products are? Now, you've seen that a whole bunch of times. You've seen that with the primary cations versus tertiary cations, right? The tertiary cation tends to be faster, the primary is slower. And you've seen it with Zaitsev eliminations. More highly substituted alkenes tend to be favored over lesser substituted alkenes. That's a thermodynamic idea. So I'm going to try and do this as carefully as I can. I'm going to start with this picture, point out some areas that you should be concerned with, and then spend half of today at least talking about what's happening here and how we're controlling things. We are starting with one diene. We are starting with the same diene in each experiment. And regardless of the temperature here, the mechanism will be the same, right? The mechanism will be the same, but maybe we can control some steps in that mechanism. If we do this, and we add a proton in that first reaction step, we produce this. So that picture isn't adequate enough to explain that entire outcome. Okay? That mechanism there, that carbocation there, isn't simply a secondary carbocation. You're adding this to make one carbocation. The whole point of this is one carbocation, right? We do not have 2 separate carbocations here. This is one carbocation. That's absolutely essential. Now, we have one carbocation that can go in 2 different directions, because it can be attacked at carbon 2 or it can be attacked at carbon 4. If we attack at carbon 2, we get what's called the 1,2 adduct. If we attack at carbon 4, we get what's called the 1,4 adduct. That's the fact. That's what you get. Now, here we go. There is something about after we get to this point that makes one reaction faster here in the blue and one reaction slower here in the red, and which makes one product more stable and one product less stable. We already dealt with the latter part of that. What makes this product more stable? The substitution pattern, right? That is di-substituted. That is di-substituted. And this one up here is mono-substituted, so going all the way back, that tells you that's less favored. It's less stable. Now, I've got slides coming up that try to explain this in words. I've got pictures, as much as you want. Right, so we've got one definition out of the way. We said that this one at the bottom is more stable. I'm going to label that as the thermodynamic product. That is the thermodynamic outcome, simply meaning it's more stable than the other ones. Those of you who take PChem, you'll learn all about that in more detail. Now, we've got to worry about this next thing, which is kinetic outcome, right? How fast things happen. How fast things happen will be dictated by where the charge is. I've drawn 2 pictures so far, in which we have some charge here, delta plus if you like, and we have some charge at the secondary carbon. Where do you think more of the charge will be? On the secondary carbon or the primary carbon? On the secondary carbon. We did this when we did epoxide, and we tried to open things up under acidic conditions, right? We'd rather have more charge at the tertiary position, which is why you got the opposite regiochemistry in those types of reactions. Well, I have a carbocation now. If I tried to draw this as a resonance hybrid, I draw that. I draw dashed lines. And then I try to draw delta plus at the end here and delta plus there, because that's where the charge is in my two resonance structures. Both of those carbons have some positive character. They need help. They need electron density. Well, it turns out more of the electron density is here. Write that down. More of the charge is there. That tends to be where the reaction happens fastest. There's no concern here really about steric environment. Everything's flat. But that is where more of the charge is built up. So that's where the nucleophile is attracted to. There is also something called a proximity effect. After we've added the hydrogen in the first step, we have to worry about where the Br is. If the first step of that reaction is to do the protonation, let me go back a second. Right, the first step is to do that, pick this up. That bromine is still very close to that molecule. That bromine is still very close to the carbon system. So now I think about two different things. Number one, more of the charge is here, and also the Br minus just happens to still be there. It hasn't swum away yet. It hasn't disappeared into space. So this now adds there. The faster of the two possibilities is adding at the second carbon, because the bromine's closer, and that's where more of the positive charge is. So that means you're going to get a faster formation of the 1,2 adduct and a slower addition at the 1,4 position. There's less charge at the 4 position because it's primary like, and also the Br minus has to sort of reorganize itself and swim around there to be able to attack that carbon. So several different reasons for why this is giving you different outcomes. What should you be getting from this so far? Formation of the 1,2 is faster, but it does not give you the more stable outcome. Formation of the 1,4 is favored. It's the more stable product, but it's also the slower reaction. Right, ready for an explanation? Why this? You can control this with temperature? Okay. Low temperature. Let's start this off. Let's just use this diagram and then go back to the pictures and sort of see if we can reconcile the two. Low temperature. Okay, you have minimized the amount of energy in this system by cooling it down as low as you can. You can go lower, but things start to freeze if you go much lower. If you get to this position on this graph, and you've cooled this thing as much as you can, where do you think most of the molecules will go over? The lower barrier or the higher barrier? Lower barrier. Low temperature. Most of those molecules are wanting to go over that lower barrier. Now, if they do, they end up down there. That's fine. But they're stuck right there. They're stuck in a valley. Because look at the size of the hill going forward versus the size of the hill going backwards. It's very difficult to go backwards if you don't have much energy. Right? You know, you went over a mountain, you went over a hill and you ended up in a deep valley. It's a pain in the backside going back up. And you minimize the chances of that by minimizing the energy. So you're trying to stop that. You're trying to stop that reverse process. What is that reverse process? Well, any mechanism, if it's a true equilibrium, has to be exactly the same. It has to be the opposite in the forward direction and the reverse direction. Yes? That's a sort of fundamental idea. So what has to happen for this molecule to go back? Tell me what physically has to happen or chemically has to happen. To go back from this bromide over here to this carbocation, Br has to break off. And is Br good at breaking off? Absolutely. And typically you see Br break it off. So we're trying to prevent this happening. We're trying to prevent going back to the carbocation stage by keeping the temperature as low as possible. That's one experiment. Okay, that's a very low temperature experiment. That's why under those conditions we got mostly the 1,2 product, because it can't go backwards because we've minimized the energy. So how do you put energy in to make this change? Warm it up, heat it up, let it go to room temperature and see what happens. So let me get rid of that again. Certainly, even at high temperature, most of the molecules go over the lower barrier to get to here. But at higher temperatures, you've given them enough energy to go backwards. The higher temperatures allow it to go backwards and to equilibrate. So the idea of the kinetic outcome, the kinetic control, is that you're trying to avoid an equilibrium. You're trying to get to the valley and stop in the valley. Whereas for the higher temperatures, you're trying to go backwards, and then go backwards again and forwards and backwards and forwards and backwards, and eventually end up with an equilibrium mixture, where the more stable outcome is favored every time. So yes, to answer your question, of course, even at higher temperatures, they'll go to the 1,2. But now they have the opportunity to go backwards. And if they're at higher temperature, we have enough energy to get over this barrier. So more molecules go over that barrier. And then you end up down here, which is the much better product, the 1,4 adduct, which is thermodynamically favored because it's more stable, because it's more highly substituted. Now, at equilibrium, you're going to get some of this, and you're going to get some of this, but you're going to get more of this because it's more stable. That's the whole point of equilibrium, right? What did he say? So we'll go to these pictures. There's the mechanism. You are adding a proton to this species. I'm going to take that pi bond, I'm going to add that HBr, and I'm going to get there. Immediately after that bond is formed, the bromide is still very close to that secondary position. There is more charge at that secondary position, so it makes sense that we get a significant amount of this. This should be the faster reaction. At low temperature, I'm trying to avoid this coming back. I'm trying to prevent the bromine from breaking off because that's a significantly energetic process in terms of going backwards. Well, I then have the possibility also of delocalization. I will get some of this, obviously. We saw the numbers there, 85 to 15, whatever it was. We did get some of the 1,4 product because not all molecules have the same energy at the same time, and some of them will go over that higher barrier. And again, in this situation, the Br minus can attack here on a different molecule, and that can give you what we call the 1,4 outcome. And that 1,4 outcome happens to be more stable. But the whole point of these things is to say at low temperature, we are trying to minimize the amount of energy in the system so we avoid going backwards if we possibly can, because these things are stuck in a low valley, and that gives you now what we call the kinetic situation, the kinetic product. And the word control means if you want to make this, if you want to make the 1,2 your major product, cool it down. It will give you the 1,2 as the major product. The opposite sense being if you warm things up. If you warm things up, you give molecules enough energy to go backwards. The leaving group can break off, you form the carbocation again, and you can equilibrate. So, you know, I don't know if that word's on there here, but this is an equilibrium system. This allows for equilibration. This type of idea allows for the Br minus to break off quite easily, and at any equilibrium is going to end up giving you the major product as the one that's more stable. So go back to that chart, right there. You should be able to explain that slide in detail. Okay? Memorize it if you want, understand it, I prefer it, and then we can start using it and you can start getting into kinetics and biochem and stuff like that, and it'll all make a lot of sense. So, low temperature, this is favored. It's not the most stable product, it's the faster formed product. We minimize the energy in that system, can't go backwards, or it's limited in its chance to go backwards, and we end up with what we call a kinetic outcome, in which this is the major product, even though that's more stable. Room temperature, you're getting close to 50-50, right? You're getting the equilibration starting to happen. Higher temperatures, you're giving the molecules enough energy to go backwards so that they can change their mind and end up in the 1,4 situation. That's a lot to handle. So there's the argument. There's the idea of control in terms of temperature. And really, that's it. I'm about to do a whole bunch of other things with dienes and with trienes that sort of, you know, they follow this type of idea. Multiple places to attack the same molecule based on delocalization. That's important there. But that control idea, you'll see it again in the future. Right, what I'm going to talk about now, the second goal for today, is to get us into the Diels-Alder reaction. This is the, I would say, synthetically, this is probably one of the most important reactions in organic chemistry. This won 2, maybe 4 Nobel Prizes overall. Diels and Alder both won Nobel Prizes, and then Woodward and Hoffman won Nobel Prizes for working out why these things happen. The Woodward-Hoffman rules. We're going to do something called a cycloaddition. And this is a situation in which, you know, this slide is a bit, sort of, some of it's redundant. I'm not going to talk about these types of reactions. I'm not going to talk about those types of reactions. But I am going to talk about this, the cycloaddition, because it gets us to 6-membered rings very, very quickly. And 6-membered rings, if you look at any of those natural products or pharmaceuticals I've been putting up over the 2 semesters, 6-membered rings are everywhere. So we have to be able to make them efficiently. So it's going to start out with a diene, as we just defined, and we're going to start out with a 1-alkene over here. And under the correct conditions, you can get these two things to attack each other. They will form, at the end, a 6-membered ring. And I'll try and show you as simply as I can how to think about this. It's going to form bicyclic systems. You're going to see odd-looking systems, but you can come up with fairly simple ways to draw these products if you're careful. So I've got a 4-atom system, and I've got a 2-atom system. And beyond that, I've got a 4-pi system and a 2-pi system. There's 2 pi electrons, there's 4 pi electrons. So we typically call this a 4+2 cycloaddition. And the product is invaluable. It's a very simple way of taking acyclic molecules which don't have anything in terms of stereochemistry and turning them into 6-membered rings which can have lots of stereochemistry. So this is very important to us as chemists. I'll make a note as I work my way through the slides here. I'm not going to cover those two. So a Diels-Alder reaction, I mean, this is one of the most studied reactions out there. It's absolutely vital for us to be able to do what we do. At the top, I have 2 pieces. 4 pi on the left, the diene, 2 pi on the right with the X group attached. I'm going to call that a dienophile. I think I have these definitions coming up. Yes, right there. I'll talk about that in a second. What's happening here is counterintuitive. Pretty much everything we have done so far has been, okay, I'm going to work out where the delta negative is in the molecule, or the lone pair, and then I'm going to work out where delta positive is in the molecule. I'm going to have one attack the other. Acid-base reactions, SN2 reactions, SN1 reactions, E1 reactions, all that stuff relied upon positive and negative things going after each other. In these types of examples, there really isn't any of that to a great extent. In fact, this molecule on the left is completely nonpolar, butadiene. This one here could be polar depending upon what X is, and it turns out polarized molecules here will actually help this reaction go faster. And the actual outcome, or the actual way this works, is that this carbon is going to bond to this carbon, and this one is going to bond to that carbon. And the arrows that we draw are fairly simple, but also quite confusing. In these examples, or in this example so far, we now have a cycloaddition. You're adding 2 pieces together, we make a cycle, that's where the term comes from. And the actual flow of electron density is beyond the scope of what we've talked about to this point, or at least before today. Because we're going to have to worry about what's really happening. Why is it this carbon attacking and this carbon attacking? And what's this arrow about? Well, that's compensating for loss of electrons to give it a pi bond back to balance the whole situation out. But we're going to have to worry about the highest occupied molecular orbital and the lowest unoccupied molecular orbital of the 2 pieces to really explain what's happening. Now, before we get this started, is this product more stable, you think, or less stable than what we start with? Thermodynamically, are we swapping good things for bad things, or bad things for good things? We're swapping pi bonds for single bonds, so this should be okay, right? This should be a favored product in terms of thermodynamics, because we are getting single bonds which are always stronger than pi bonds. How it happens is fun, but we first off have to be careful with the fact that it can happen, and it's favored. In terms of the reaction profile, this is about as simple as it gets. This is like the E2, this is like the SN2 from last year, straight up and straight down. Why do we have to go up? Well, you've got bonds being formed and bonds being broken. That always costs energy. And you think about when we talk about the orbitals involved, you're going to have to dump some electron density into an antibonding orbital to make this work. That will destabilize the system, which will then reorganize itself to become more stable. In other words, it has to go up, and then it has to go down. Simple as that. The transition state itself is really, really well put together. It's really symbolic of what's to come in the near future, where we have 6 pi electrons in a cycle. Right? 6 pi electrons in a cycle is really, really going to be important in the near future. So keep an eye on that. It's a very simple reaction. Okay. 6 pi system here. Cyclical system, 6 pi electrons. This is going to be important when we get to benzene chemistry. Now, the argument here about how stable this thing is really important. We've got to worry about thermodynamics, we've got to worry about the components of the delta G equation again, and we've got to worry about enthalpy versus entropy. What we're doing here is taking 2 acyclic pieces and bringing them together to make a cycle. So delta G is very important right now. In this system, what do you think about, we already asked this question, what do you think about delta H? Is the product more stable or less stable than where we started? More stable, right? Don't forget delta G has to be negative. So in this case, delta H is fine. What about entropy? This should be something we should be able to handle by now. Look at these starter materials. Look at those products. What do you think about the product versus the starter materials entropically? There's less possibilities of rotations, there's less possibilities of expressing energy in that system, and so that is entropically disfavored. Now, to make it work, think about going all the way back to last semester, where we've got the ideas of making alkenes and that sort of stuff, and eliminating from alcohols to make alkenes, and all that idea of how we make it work. This is going to go. This term outweighs this term. So in this case, it's thermodynamically favored enough not to have to worry about delta S being a problem. Right? It's a classic MCAT, PCAT, whatever type, GRE type of question that you see. This reaction is entropically disfavored because you're making a cycle. You're tying the molecule together, which prevents rotations. That's going to be a negative change in entropy. As opposed to the starter materials, which are acyclic, free rotations all over the place, and therefore much more favored in terms of entropy. I thought this is a great reaction because you can make cycles. In terms of the energy involved, it is thermodynamically favored, but it's not entropically favored, but the thermodynamic factor wins, and it works. Now, what we have to worry about is the types of group attached. There's just a slide showing you exactly what I just said. In terms of the bonds broken, you're swapping pi bonds for single bonds, and it's going to work for you. What we need to worry about is what X happens to be, and then start to use this, and start to use it to make some interesting products. In this case, I've used the word diene from the beginning of the chapter, but I haven't used this term here. I haven't yet used that term. What do you think a dienophile is? Something that likes dienes, right? Electrophiles like electrons, nucleophiles like nuclei. Dienophiles are really fond of dienes. Yeah? They get along well. So you mix these two things together, and away we go. Now keep an eye on this. How you actually run this thing. Alyssa, this sort of starts to answer your question. You have a diene and you have an alkene. Not very polar. No electrostatic interactions or attractions between them at all. But it still works. But look at the temperature you have to run this at. And this actually is quite a difficult reaction to run between butadiene and ethylene. Because one's a gas and the other one's a low boiling liquid, and you have to put this thing in a pressure tube, and you have to be very careful you heat this thing up and make these things add together. But it will go. And the reason you put them in a pressure tube quite often is to get rid of that entropic factor. They don't necessarily want to be together. You squeeze them. You make them go together. So the yield here, the yield is very low. It's not a great experiment. As opposed to the right-hand side, all of a sudden, we can start to do these things at much lower temperatures and get very, very good yields. The idea now is that you've introduced an electron withdrawing group. That is a delta positive carbon. That is going to pull electron density out of that pi bond. Now, without losing anybody, because this is important in terms of the explanation, if you start to change the electron density in that pi bond, you change the energy of the pi bond. Okay? You change the energy of the pi bond. And the pi bond itself, the electrons are in the lowest unoccupied molecular orbital of that system, and you're going to change its energy. We drew some diagrams before. We had an HOMO and an LUMO and stuff like that. You're going to perturb the energy of those electrons. And it turns out the electron withdrawing groups on the dienophile bring the two pieces closer together in terms of their energies. They're going to bring the LUMO of the alkene closer to the energy of the highest occupied molecular orbital of the diene. I have a diagram to show that in a second. The electron withdrawing groups are great at doing this. They just bring the energies closer together, make the reaction that much easier to do. In terms of what we can use, well, you've seen a whole bunch of these things. You've seen a whole bunch of these types of systems in which we have aldehydes, in which we have esters, carboxylic acids, and nitriles. Every one of those groups, especially think about what's about to happen with the benzene chemistry. Delta plus here, yes. Delta plus here, absolutely. Delta plus there, absolutely. Delta plus there, absolutely. That's the key. On the other hand, electron donating groups will slow things down, make it more difficult. So electron withdrawing groups on the dienophile are going to make the reaction easier to do. And you can't get better than 100%. We have a 4 plus 2, and it's not this that reacts, it's the diene alkene that reacts, and you snap the two together. Now, the mechanism of this, again, be careful. It doesn't really matter which directions the arrows go in, as long as they form a cycle. As long as they go in a cyclical sense, so that one goes to here, the next goes to here, the next goes to here. Go in the same direction every time. And as you run this reaction, every time, you get a 6-membered ring. You do not get 5-membered rings. You do not get 7-membered rings. You get 6. So I have here an example of the dienophile changing its structure. Again, typically, and you might write this down now that it's been mentioned, X we're used to seeing as halides. In this case, X is usually not a halide. They're electron donating. They will slow things down, if anything. So in this case, we're talking about carbonyls, we're talking about nitriles, C-triple bond N, stuff like that. What I have at the top are 2 experiments that will give you some idea of the mechanistic. Why am I drawing those arrows the way I am? Why not draw a stepwise mechanism? Why not make an argument about something with a carbocation? Well, we can look at these 2 experiments and hopefully get that pretty quickly. Look at the starter materials here. Look at the nature of that alkene. What would you say that is in terms of its stereochemistry? Cis, right? And what's the relationship of those 2 groups in the product? Cis. Now, what does that tell you about the mechanism? It's concerted. It's concerted, right? We dealt a lot with that last term. The fact that there's no opportunity for rotation around that system means that you're not getting a carbocation, you're not getting a radical, because those things can rotate. This thing is concerted, absolutely. So if I draw this here, that's an attempt to show a concerted process. So we've got to be happy with the idea that the stereochemistry of the alkene is retained in the product. Okay? That's important to understand why the mechanism is concerted and why I'm not drawing carbocations and things like that. That's just consistent with what we've seen over the two terms. Now, at the bottom, this is an example showing you that the dienophile, its character can be quite diverse. It can change from an alkene to an alkyne. Because don't forget, alkynes are even more reactive than alkenes. The pi electrons are not held as tightly. And we have two sets of them. So therefore, they should be reactive too. And in this case, with alkynes, we often soup up their reactivity by having two electron withdrawing groups on there. All right, and this material is quite useful for that. So the mechanism, again, simply 4 plus 2, and we get a 6-membered ring. But because we started out with 2 double bonds on the diene, we've got one of them left. That's where that extra pi bond comes from. That's okay. You started with 2, you got 1 left. Now let me see, just as we get towards the last couple of minutes here. Notice where the pi bond goes. The pi bond always goes in the middle of what was the diene, every time. In this case, the pi bond ended up in the middle of the 4 atoms that were the diene. Now the product here, Michael's asking this question. If I were to add some nucleophilic reagent, then you're going to probably add to these species here, the carbonyls. If you'd used it, lithium aluminium hydride, right? There we go for the carbonyls. There will be chemistry later when we attack this, but that's a ways off. But right now, I would argue that this reaction allows us to very easily go from simple materials to quite complex systems